Hi, I'm Andres Quesada, and I'm gonna show you how to work problem number 80. They're saying suppose David puts a 6.6 kilogram rock in a sling of length 1.5 meters. So right from the top, I know that my mass is going to be 0.6 kilograms, and my diameter is going to be 1.5 meters. That means my radius is going to be half of the diameter, which is 1.5 divided by 2. So I got 0.75. 0.75 meters. Great. Alright, let's continue reading. And begins whirling a rock in a nearly horizontal circle. Cool thing. Accelerating it from rest. So since it's from rest and we're working with rotational motion, we're gonna know that my initial angular velocity is going to be 0 radians per second. Not square. Okay. At a rate of 75 revolutions per minute. So that means our final angular velocity is going to be 75 RPM. Now, since we're working with radian per second, I need to change this to radians per second, and that's simple. You just need to do 2 pi multiply it times 2 pi over 30. All right, great. Let's do it. All right, so we have 75 times 2 times pi divided by 30, and I get 15.71 rounded, of course. 15.71 radians per second. All right, let's keep on reading. After 5 seconds, so our time is going to be 5 seconds. Great. What is the torque required to achieve this feat? All right, so they're asking for torque. Easy. Great. All right. So for sure, 2 things I can find right now based on the information I'm given is my moment of inertia and my angular acceleration, right? My rotational acceleration. I'm gonna start off first with my moment of inertia, and my moment of inertia is going to be equal to mass times radius squared. So I'm just going to plug it in. It's real simple. My mass is 0.6 and my radius is 0.75 squared because it's part of the formula. And I'm just gonna put this here away. And I'm just gonna plug it in. So I got 0.6 times 0.75, since it's squared, to do it 2 times 0.75, and I get that. So my moment of inertia is going to be 0.3375. Alright. Good. Now I can find my angular velocity, which is the same thing as regular linear velocity, but we're just going to use rotational method symbols, which is going to be our final minus initial over time, and my final is going to be, I already know it's 15.71 minus 0 over my time, which is 5. And he's going to plug it in. So like put a shortcut over here. I'm going to go to history, and it's going to be that minus 0, which is that, and I'm gonna divide it by 5, which is my time. Alright, and that will give me 3.14 pi. What? Oh, how nice. Pi. That's interesting. Okay. Yeah. Oh, radians per second squared. Alright, so I got my moment of inertia and my acceleration. Now I can easily find my net torque, which is very simple. The equation is going to be net torque is equal to moment of inertia times acceleration. which is it's the same thing as regular linear linear version of this, which is force times mass times acceleration. It's just like in different variables. All right, you can plug that in, which is fairly amazing, because I already have all these two present, which is 0.3375 times 3.142. All right, and here we go. So you're gonna have this number over here, which is my acceleration, and I'm gonna multiply it by go back to history, and it's gonna be 3. There it is, this number, and I will get 1.06. Looks good. 6 meter newtons, not newton meters, meter newtons. That's my answer. All right, now I finished reading the answer. The question: where does the torque come from? All right, so the torque comes always from an external force, right? So the external force is right in this case is going to be the rock, because it's the only thing that's actually affecting the system. So the rock right here is the external force and it's exerting a force of gravity. So torque comes from the rock. Nice. Thank you.